So I'm going to talk about functions today. I'll talk about function call and function return, the stack segment, how we can preserve registers across function calls, how we can allocate an array on the stack, and I will show some examples about like bubble sort and recursion. Right, so we know functions. A function is also called a procedure. It's an abstraction, okay, which is used in high-level programming languages, and it allows you to break down a program into functions. For example, many old programming languages, like the C programming language, supported functions. So a function is a block of instructions, and it can be called at several different points in the program. And it allows the programmer to focus on just one task at a given time, and it allows the code to be reused. So this is really the idea of functions, and you can build libraries of functions, and you can reuse these functions in different programs. This is really the idea of a function. So the function is self-contained. It can receive parameters, it can return results, and this makes the function general, okay? So it can be reused in different programs. Now, the function that initiates the call is called the caller. So the caller is going to initiate the call to a function. And the function that receives the call is called the callee. Okay, so the caller, it's the function that initiates the call. And the callee is the function that's going to receive the call. Okay, so this is called the callee function. And when the callee function, when a function finishes execution, it is going to transfer control back to the caller. Okay, so the caller is going to call, let us say we have function f calling function g. F is called the caller and g is called the callee function. And when g finishes execution, then it's going to transfer control back to the caller function. A function can receive parameters. I mentioned this earlier, and it can return results. And the parameters and the results, this is what we call the interface, okay, between a function and the rest of the program. Okay, so this is what the function is. You already have seen functions in programming languages, in high-level programming languages. So I'm going to talk in this presentation how we can define functions in assembly language. Now, to execute a function, the caller has to do the following. It has to put the parameters in a place that can be accessed by the callee, and it has to transfer control to the callee function. Okay, so it has to pass the parameters first, and then it has to initiate the function call. And to return from a function, the callee has to do the following. It has to place the result, okay, it can be one or more results, in a place that can be accessed by the caller. And then it has to return control back to the caller. Okay, so again, we have to transfer control. Okay, and it has to transfer control back to where the function call was made, to the next instruction in memory after the function call. Now, to put the parameters in a place that can be accessed by the callee, okay, these can be placed in registers. So we can use registers. These are the fastest memory elements, and we can use them to pass parameters and to return results. So the MIPS architecture and many architectures, they prefer registers over memory. However, if you are dealing with a large number of parameters, or you are dealing, let us say, with arrays, you cannot really place the arrays in registers. You have to place them in memory, and you can place the address or the addresses of these arrays in registers, and then you can pass them to a function. So in the MIPS architecture, we use registers, okay, to pass arguments if you are dealing with simple arguments. And these registers are called the argument registers A0 to A3. So using these 4 registers, we can pass parameters to a function. And if a function would like to return results back to its caller, then it can return them in V0 and V1. These are called value registers. So A0 to A3, these are called argument registers, whereas V0 and V1, these are called argument registers. So we can pass the arguments in A0 to A3, and we can return the result in V0 and V1. Now, in addition to these, there is a very important register, which is called the return address register, which is RA. Now, this return address register is very important because it will contain the address of the next instruction appearing after the call instruction. So this register will contain the address of the instruction that we should return back to it after finishing the function call. So we call it the return address register. Okay, this is very important because the function needs to know where to return after finishing the execution of a function. Now, in the MIPS architecture, the call instruction is called the jump and link. Jump and link is the call instruction. This is how we write it. Jump and link does a jump, and also it does a link. So it does 2 things. It does a jump to call a function. Okay, so we have to jump to the first instruction inside the function. This is how we make the function call, but it's not a normal jump, because it also does a link. And the meaning of a link is going to save the return address in register RA, which is register number 31. So the return address will be PC plus 4. So PC plus 4, this will be the address of the next instruction appearing after the jump and link, and this will be saved in register 31. Okay. So we have to save the return address. So this instruction has to save the return address in register number 31, because without this address, we cannot have the function returning back to its caller. So this is the jump and link instruction. So it does a jump, and also it saves the return address in register number 31. Now, on the other hand, we have jump register, or JR. Okay, this is called the jump register instruction. This is used to return from a function call. So all what it does, we can jump to register 31 that contains the return address, and this way it can return from a function call. Now, in fact, jump register, it can jump to the address in any source register RS. So when you write the instruction, okay, you can say jump register, and you can specify a source register RS. And what it does is going to change the program counter to become the address which is in RS. So it's going to change the value of PC to become RS. So these are the 2 instructions which can initiate a function call and to return from a function. These are shown in the table below. Okay, you can write it like this: jump and link, and you can write a label. So what it does is that it's going to save PC plus 4. PC plus 4, this will contain the address of the next instruction, because PC itself contains the address of the jump and link instruction. So PC plus 4 will be the address of the next instruction appearing after jump and link, and this address will be saved in register 31. And at the same time, it's going to jump to label. Notice that its format is of the J type, the jump type. So we have the opcode equal to 3. This indicates that the instruction is jump and link. And there is a 26-bit address, okay, for this given label here. Okay, so for this label, there will be a 26-bit address inside the instruction. If you would like to return from a function call, we use the jump register instruction, and we jump here to the register RS. And this means that we change the program counter to become the value of register RS. Okay, so this is the jump register instruction. So by changing the PC to become RS, we can choose RS to be register 31, And if we jump to the address inside this register, we can return back to the caller. So the jump register is essential to return back from a function call. Notice that jump register is of the R type, the opcode equal to 0, and there is a unique function code. And all that it needs is just RS. Okay, so RS here is a source register containing the address where we would like to jump. So it is an indirect jump because we are jumping to an address which is stored inside a register. Okay, it's different from the jump itself because we jump to a label. So here we don't really have a label because we don't know where to jump. So we jump to the address which is stored inside a register. Okay, so this is why it's called a register indirect jump. There is also a third instruction which is called the jump and link register. So jump and link register, it does two things. It does a jump register and also it does a link. So this is how you write the instruction. So you specify RD, which is the destination register, and RS, which is a source. So what this instruction does is going to jump to register RS. It's like a jump register, so PC becomes RS, but also it does a link. RD and specify RD, it's equal to PC plus 4. So PC plus 4 is nothing but the return address. Yes, Mustafa.
Doctor, are these registers that can be accessed by the caller, are these B0 and A0 and so on?
You can use any register in the register file. So we have 32 registers, and you can use when you are using registers in these instructions. So when I say RS, it can be any register. When I say RD, it can be any register. Okay. I will show you an example about this. Yes, Mustafa.
Because in the previous lecture, you showed a function that uses V0 and A0.
Yes, so we're going to use actually A0 and V0. So we'll use actually A0 to pass an argument to a function. We use V0 to return a value from a function. And we can use register 31 to store the return address, of a function. This is where we would like to jump, when we would like to return back from a function. Khalid? Yes, Khalid.
Yes, Doctor. What's the difference between these instructions and the normal jump that we know?
The normal jump is going to jump to a given label. You cannot use it, to call a function or to return from a function. Because if you use it to call a function, if you just say jump to label, and label will be the address of the function, fine, you can actually jump to the function, to the first instruction, but you don't really know where to return. And the reason why you don't really know where to return, because the function can be called from different points in a given program. So you can actually call the function multiple times in different places, so you don't really know the return address of a given function. So for this reason, if a function wants to return, it has to know where to return. And we cannot really use the jump instruction to return from a function, because the function can be called in different places, and the function does not really know, who called it and where to return. So for this reason, we use jump and link, because the link part is going to save the return address in a register, and we use jump register, to return from a function call, because we store the address inside a register and we jump to this address in the register. I'm going to show you an example that illustrates how you can write functions and what's the meaning of these instructions. Jump and link register is a combination of jump and link and jump register. So it's also useful in some programming languages where you would like to have the address of a function itself. The address of the function is known at runtime. For example, in object-oriented programming languages, the address of a function might not be known to the compiler, and it's only known at runtime, and therefore you would like to place the address of a function in a register. So you use jump and link register to call the function and also to save the return address. Right. So let us take a look at this example. Okay, I have an example here about a swap function. So this swap function is written in a high-level programming language, okay, which is C. So this swap, okay, has two parameters, V. V is an array of integers, and it has K, which is just an integer. So you can see that these are the parameters, these are the formal parameters of the function swap. And inside the function swap, there are three statements, and these statements are going to swap two elements of the array V at index K at index K plus 1. So notice that here we are reading V of K plus 1, we are writing V of K. Here I'm reading V of K. Okay, here I'm writing V of K. Here I'm writing V of K plus 1. So we need two load instructions here to load V of K and V of K plus 1. And we need two store instructions to write V of K and V of K plus 1. But when we write them, we swap them in memory. So this is the function swap. This is very useful if you would like to sort an array and you would like to swap, let us say, two consecutive elements inside the array at index K and index K plus 1. So the function is given to us. So what we need to do is that we need to translate this function from C into MIPS assembly language. So how do we translate this? I'm going to write the function, and then later I'm going to call the function swap. Okay. So let us first try the function swap. So the function swap can be called from any place in your program, and therefore it has to be written, okay, to be self-contained, to receive arguments, and to be able to return back to the caller. So we are going to use two arguments, and the arguments, according to the MIPS assembly language, the convention is to pass the arguments in registers A0, A1, A2, and A3. But in this case, we only have two, so we only need two registers, A0 and A1. So we are going to use A0. Now, A0 cannot store the entire array V because the array V is large, okay? And we don't know how many elements exist inside this array. So we cannot use a register to store the entire array, but we can use the register to store the address of the array V. Now, the array itself is in memory, okay? But you can have the address. The address is just like an integer. The address is just an integer. So we store the address itself in register A0. And we store the index K inside another register, which is A1. So A0 and A1, these are called the argument registers. So this is register number 4, and this is register number 5. Okay, so A0 is register number 4, and A1 is register number 5. So the caller, before making the call to the function swap, the caller has to pass the address of the array in register A0, and the caller has to pass the index K in register A1. Now, in addition to these two registers, also this function, when it reaches this closing brace here at the end, okay, it wants to return. It wants to return, although there is no return instruction here, but by default, when you finish the execution of all the instructions inside a function, you have to return back to the caller. And in order to return back to the caller, there must be an instruction that returns back to the caller. So even though you are not using the return statement, by default, the function has to return. Now, where does it return? Where does it jump? It does not know. It does not know where to jump. Why? Because we don't really have a fixed label. So we cannot really use the jump instruction to jump back because it does not know who called this itself. Yani who called this function? We don't know who is going to call this function. It can be called from any place in your program. And for this reason, you cannot just use the jump instruction because you are not really jumping to a fixed label in the program. So in order to do this properly, we have to save the return address in a register. And this register is register RA. We call it the return address register. And this return address register is register number 31. It is the last register in the register set. Okay. So we save the return address in register RA, and therefore we are going to jump to this to the address which is saved in this register. Okay, and this way we return from the function. Of course, it's a responsibility of the caller to save the return address in RA. So the caller is going to use the jump and link instruction to call the function and to save the return address in RA. Now the translation becomes simple. I'm showing it here to the right. So the swap function starts at this label. So every function will have a label. Okay, this will be the name of the function. And now what we need to do is that we need to have 2 load instructions and 2 store instructions. But to load the value of VK and VK plus 1, we need to do address calculation. So we need to calculate the address of VK. So the address of VK, it will be what? It will be K multiplied by 4 plus the address of V. Now K itself is A1. So we need to multiply A1 by 4. So I can use a shift left instruction. So this shift left instruction is going to shift the value of K, which is A1, by 2 bits. This will be multiplication by 4, and places this this address, let us say, in a temporary register, places this number, sorry, in a temporary register T0. So this is K multiplied by 4, and we are placing the result in T0. Now we take T0 and we add it to V0. Sorry, we add it to A0. A0 is the address of the array V. So we take T0, which is K plus 4, and then we add it to the address of V and place the address in T0 again. So now we get now in T0, after doing this addition here, we got in T0, it's the address of V of K. Okay, because we are adding the address of the array V plus K multiplied by 4. So this will give me the address of V of K. I can just write it, okay, using my pen tool, just to make it clear. So I can here write that now T0 becomes, let me just use my pen tool. Yeah, let me write it down here that this is T0. What we are calculating here is the address of V of K. Okay, that's the address of V of K. Now the address of V of K now exists in T0. So I'm going to use T0 here as the address to load the value of V of K into T1. So T1 now contains the value of V of K. And by adding 4 as a displacement to T0, we can load the value of V of K plus 1 into T2. So now T2 here contains the value of V of K plus 1. So K plus 1 here, because we are indexing. Now notice that K plus 1, this one becomes 4 because it's an array of integers. You can see that here V is an array of integers. Okay, so each element in the array is 4 bytes. So by loading now the value into T2, so we have 2 values in T1 and T2. T1 is the value of V of K, and T2 is the value of V of K plus 1. Now, all what I have to do is just to swap them in memory. So we are swapping them in memory. So this is why I need 2 store instructions. So I'm going to store the value of T2 at the address in T0. So the value of T2 will be stored at the address, okay, of VK. So we are storing the value of VK plus 1 in memory at the address of VK. And we are storing the value of T1, which is VK, the value of VK. We are storing it in memory at the address of VK plus 1. Now, once we are done, we have swapped the 2 elements in memory, then we can return. Now, in order to return, this function has to execute this instruction, jump register RA. This is my return instruction. Why? Because the return address is stored in this register RA. Okay, so the RA will contain the return address of the function swap, and therefore we have to say jump register to RA. Is this clear?
Doctor?
Yes, Todd.
JR, it will return us to where we are called the function.
Exactly. It's going to return to wherever the function was called. So this is why the address is not fixed. The address is a variable, and the address is stored inside register RA. Okay?
Okay.
Now let us take a look here, okay, at the call return sequence. in this slide. Now, suppose that I have a function which is called the caller. So the caller is going to call a function swap. So this is my caller function. Swap is my callee, okay, which is the function that is going to be called. Now, the caller, before making the call to the function swap, is going to load the address of some array A in memory, is going to load the address into A0. Okay, so the address of the array will exist. Okay, so this is the address of the array will be in register A0. So these are the arguments. And it's going to load the index. So this is load immediate. The index here will be 10 into A1. Okay, so it's going to initialize 10. A1 becomes 10. So A1 here is the index K, and A0 is the address of the array. So it's an array A. So suppose I would like to call the function swap, and I would like to pass here 2 parameters. A is the address of the array, and 10 is the index. Okay. So the caller has to pass these arguments or these parameters. These are the actual parameters that it has to pass them in these 2 registers, A0 and A1. Now, after it has passed the arguments, then it can make the call to the function swap. So jump and link is going to make the call to the function swap. It does 2 things. So by doing jump and link, this jump and link, it does a jump, but also it does a link. It does 2 things. So it will jump, okay, to the first instruction, okay, inside the function swap, to the first instruction, which is this shift left logical. And at the same time, is going to save the return address in register RA. Register RA is the register number 31. It is the last register in the register file. Right. So the function swap is going to execute all of these instructions. It's going to swap 2 elements inside the array at index 10, at index 11. So 2 integers will be swapped inside the array. And then it's going to reach this last instruction here, jump register RA. When it reaches this last instruction, jump register RA, it's going to return back to the caller. It's going to look at the value of register RA and change the program counter to become the value of this register. So by doing this, it's going to return back to the caller, to the instruction that appears here immediately after the jump and link instruction. So after finishing the execution function, return back to the caller at the instruction that appears immediately after the jump and link. So jump and link does the call, jump register does the return. So this is the call return sequence. Okay. Khalid?
Yes, Doctor. I have a question. Yani, might sound a little bit silly, yani, but
No
why we are shifting? Why don't we add 4, for example?
Because this is an array of integers. It's not an array of bytes. So each integer is 4 bytes. Each element in the array is 4 bytes. And this is why we have to shift. You have to multiply the index by 4 before adding it to the address. This is address calculation. Okay. So the address let me just write it down here. Remember how we did address calculation? So the address, okay, so if I would like to calculate here, let me just use my pen tool again. So the address of the array A at any index K is equal to the address of the array A plus K multiplied by 4. So I have to multiply K by 4 because each element is 4 bytes. K is the index. K multiplied by 4 will be the number of bytes, okay, from the beginning of the array until you reach this element in the array. Yani, for example, if K is equal to 1, if you would like to go to the element at index 1, you have to add the address of the array plus 4 bytes. If you would like to go to the element at index 10, you have to start at the address of the array plus 10 multiplied by 4. You have to add 40 bytes. So because each element is 4, you have to multiply by 4. This is why we are multiplying the index, which is in A1. We are multiplying it by 4. So this is the purpose of the shift left logical instruction. And the purpose of the add is to add the address of the array A. Is this clear?
Yes, thank you.
Okay, Ali.
Doctor, what if we want to pass more than 2 parameters? I mean, I see here
We can use
A0
A2,
takes the
and we
array.
can use it. So we can use, if you would like to, you can pass up to 4. According to the MIPS architecture, you can pass up to 4, A0, A1, A2, A3. And some revisions allow you to even to pass more in registers. Typically, functions have a small number of arguments, but if you have a very large number of arguments that you would like to pass, you can use the stack. I will talk about the stack to pass additional arguments on the stack in memory. So you can pass them in memory on the stack. Okay. And so we have to use memory. If you cannot, if registers are not really enough to pass all the arguments of a function, then you have to use memory. Okay. So let me show you
the function itself. We should know which register are gonna use.
Yeah, so when we define a function in a high-level programming language, we look at how many parameters, okay, this function has. If it has only one parameter, we use only register A0. If it has 2, we use register A0 and A1. If it has, let us say, 4, we use A0, A1, A1, so on. So it depends, of course, on the function. So in this swap function, we only had 2 parameters. So we used A0 and A1 to pass them, to pass the arguments in these 2 registers. So the argument means parameter, okay? So when I say argument, it means parameter. Okay, so the arguments of a function, these are the parameters of a function. So we use registers because registers are faster than memory. But if you have a large number of parameters, then we have to use memory in addition to these registers. Yeah, we can first use these 4 registers, but suppose that a function has more than 4 parameters, then we have to use memory in addition to these 4 registers, A0 to A3. Okay? Okay. And the return address is also placed in a register, which is register RA. Right. So these are the details of a jump and link and jump register. So what I did is that I typed the program. I used the Mars tool to type the program, and I used the assembler to translate, okay, the program. So first I wrote the caller. So the caller code is shown on top, okay, load address. So this is the load address instruction, which was shown here in the previous slide. This is my caller. This is my callee function swap. So the swap function is shown below. Okay, so the swap function starts at this address here in memory. I'll use my highlighter again. So when I say here swap, this is my swap function. And this is where it starts in memory at this address. So swap is this corresponding memory address. And these instructions exist at these addresses. So this is the address of the shift left logical instruction. Notice that register T0 is register number 8. A1 is register number 5, and so on. Notice that the load address, this is a pseudo instruction. It's not a real instruction. So load address is a pseudo instruction. To load the address of the array A into A0, it requires the address consists of 32 bits. So this is why it uses 2 instructions, load upper immediate and or immediate. Okay, so this is the upper 16 bits of the address, and 0 will be the lower 16 bits. So the complete address consists of 32 bits, but we are loading the upper 16 bits, and then we are ORing it with the lower 16 bits. The lower 16 bits turns out to be 0. It depends, of course, where the array is located in memory. So you see that LA is a pseudo instruction, is translated into 2 basic instructions in the MIPS architecture. After that, I would like to say load immediate. This turns out to be or immediate, just or immediate. Okay, to load the constant 10 into register A1. Register A1 is nothing but register 5. Register A0 is nothing but register 4. And I have a jump and link. Now notice that jump and link, it is called jump and link swap. This is how you write it in assembly. But after translating swap, it becomes this number. Of course, jump and link will have an opcode. I'm not showing the opcodes here. Okay, I'm just keeping it simple. Okay, so the opcode of jump and link will be the number 3. I'm showing here the 26-bit address. So the 26-bit address turns out to be this number. But really, I would like to jump to this address. Okay, so really, okay, so swap itself, let me use my pen tool again. So swap will be this number. And this number becomes this address, because this is the address that corresponds to the swap label. Now, what will happen is that, okay, when this instruction is executed, jump and link, it does two things. It extracts the 26-bit immediate. Now, we know that the addressees of instructions are always multiple of 4, because the instructions are aligned in memory. And because they are aligned and the addressees, each instruction is 4 bytes. So therefore, the addressees are multiple of 4. So the least significant 2 bits of the address is always 0, 0. So if you take this number and you shift it to the left, if you take this 26-bit immediate, which is inside the jump and link instruction, this number here, and you shift it to the left by 2 bits, as shown here. So you take this number and shift it to the left, you get the address. So by inserting 0, 0, okay, you get this address, which is the address of the shift left logical instruction. This will be the address of the first instruction inside the swap function. So this is what the CPU will do. This is called pseudo direct addressing. It's going to extract the 26-bit immediate from the jump and link instruction and convert it into a memory address by inserting 0, 0 at the end. It's a very simple thing that is done by the hardware that is going to compute the address from the 26-bit immediate. Now, once we have the address, it's going to jump, okay, to the first instruction that exists inside the swap function. But at the same time, it's going to link. It's going to store the return address. So the jump will go here. And at the same time, it's going to link. Now, the link means this address here. This will be the address of the instruction. Notice that the address of a jump and link is shown here. Okay, it ends with 2C in hexadecimal. Now, if you add 4 to 2C, you get 30. So notice that all these addressees are shown in hexadecimal. It's always preferable to use hexadecimal for memory addressees. Okay, notice that these addressees are 32-bit addressees. Okay, and therefore it's going to store the return address in register 31. So notice that the value of register 31, this is the return address register. It's the address of the instruction that appears after jump and link. So really, it does not really matter where you call the function. It can be called at any point in the program. And the return address is the address of the next instruction that appears after the jump and link. So this address is saved by the jump and link instruction. It is saved in register 31. This is what we call the return address register. This register 31. Automatically, the hardware, the CPU, when it executes jump and link, it's going to save the return address, the address of the next instruction appearing after jump and link. Okay, this address will be saved here all the way into register 31. You can see its value. Okay, sorry, it's shown here inside the register. Okay, it is saved inside the register. Fine. So after finishing the execution of the swap function, we reach this last instruction, which is jump register RA. Remember that RA is register 31. So we want to jump to this address, which is stored inside register 31. So how do we jump? The CPU is going to look at the value of register 31 and then jump back to this address. You just clean up everything. You can see that the value of this address inside register 31 and jump to this address. By jumping to this address, it's going to return back to the caller. So this is how the return is done, by this jump register instruction. We cannot just jump to a label because I don't know where the call was made. So for this reason, we need this jump register instruction. Is this clear? These are low-level details of jump and link and jump register, and it will show you how the function return takes place. Okay, good.
Yes, good.
Here's a second example. I'm going to write a function which is called toLower that is going to convert any character ch to lowercase. So we are going to check if the character ch is a capital letter, okay, from A to Z. So ch greater than or equal to capital A and ch is less than or equal to capital C, convert it. Now, how do I convert it? I say ch minus character A and then plus lowercase a. Okay, by subtracting capital A, so capital A becomes 0, capital B becomes 1, and so on. And then by adding it to lowercase a, we're converting it to a lowercase letter. Okay, this is just a simple trick how to do the character conversion. And then at the end, just return ch. Now notice that this is my this is an if-else statement which is written inside the function toLower. This is a translation of the function toLower. So if I have to check, okay, if ch is greater than or equal to capital A. In other words, if it is less than, so I use a branch less than, if A0, now notice that I only have here one parameter. So this parameter ch must be passed in A0. So A0 is the parameter ch. And since we are returning a character, this character here must be returned in V0. So look at the function, how it's written, and you will know that actually what are the parameters and what are the results. In this case, we only have one parameter, which is A0, and I only have one result, which has to be passed in V0. So therefore, we are going to here to execute this if statement. So we use a branch. So if ch here, okay, which is A0, is less than capital A, go to the else part. And the else part, we can move the value of A0 into V0. It says return ch. So ch is A0, move it into V0 because we are going to return it in V0, and just jump register to RA. That's it. This is my else part. Now, this is if A0 is less than capital A or it's greater than capital Z. In other words, if it's not a capital letter, go to the else part. If it is a lowercase, sorry, if it is a capital letter, this will be for okay to A result in V0. Now the difference capital A, sorry, lowercase a minus capital A is equal to the number 32. So by adding, okay, 32 to A0 and placing the result on in V0, we have converted the character to lowercase, and we can just place the result in V0 because I would like to return it in V0 and just jump to register, okay, jump register to RA. RA here is my return address so that we can return back to the caller. So this is a second example of a function, okay, a very simple function that has an if statement. And notice that this function is going to return a result. Any question?
Yes. Why we say add V0? We use the register V0 with an A0 with 32. I mean, why you use register V0 here?
Because the result has to be passed, this character here, that when you say return, the value of this should be returned in V0.
Okay.
So when I say return, it means whatever actually you are computing here, this must be returned in V0. This must be returned in V0. The result here must be returned in V0. Okay. This ch here is passed in A0. Okay.
Shouldn't be V0 initialized, for example, by 0. Maybe before I call this function.
Well, we have
to use the
no need, because the value of V0 will be defined by the function. You don't even have to initialize it. Okay, so so whether ch is a capital, if it is capital letter, you return this value. If it is not, then you just return the value of ch. So in both cases, you are going to return. Okay, so whether you are executing the if part or the else part, you are going to return some value in V0. Notice that this is the if part here, this is the else part, okay, in the assembly language.
Okay.
So that's it for today. Okay, so I just introduced functions, function call, and return. In my next lecture, I will talk about the stack segments,